video is going to look at how we can find the gravitational field or acceleration due to gravity on different planets. So first we need to know what is gravitational field strength. And so far we've discussed the gravitational force between two objects, and we've learned to calculate the magnitude of that force using Newton's law of gravity. The equation follows what we call the inverse square law, where the strength or intensity falls off at a rate of 1 over the square of the distance. And this graph down here is what that inverse square law looks like. So if you see a graph that looks like this, it's an inverse square law. Now, another way of representing it is like this. So if you think of something that's moving out or that has an inverse square law, one of the easiest things to think about is maybe light. So if you have a bit of light shining from this point right here, well, the farther it gets, the more surface area it actually has to cover with the same amount of light. And the farther away, it gets even bigger and bigger according to the square of the distance. So we only have one block at a distance r. Now it's 4 blocks at 2r and 3 blocks at, 9 blocks when we get to 3r. So this is what the inverse square law looks like, and this is how it is with gravitational force or gravitational field. So what is gravitational field strength and how does it relate to gravitational force? The gravitational field strength at a point in space is measured by dividing the gravitational force exerted by the field on a test object at that point by the mass of the test object and has the same direction as the force. This is the definition, what you need to know, the essential knowledge directly from the College Board. Yes, it makes me go cross-eyed too. So let's look at the simplified version. So in the picture below, we have a picture of the Earth, and these lines going into it are what we would call gravitational field lines. And what they do is they show the direction of the gravitational field. Basically, it's always pulling down towards the center of the Earth. The density of the field lines indicates the relative strength of the gravitational field. So when I'm looking closer to the surface, you're going to see that the field lines are closer together than, say, when I come way out here. They're going to get farther apart. And we can see that when we look at this gravitational force graph also. So when we have this graph of force versus distance, I can replace force with field, and the graph is going to be exactly the same. The field is also going to get less with the square of the distance. It also follows the inverse square law. So when it talks about a test object, let's make it simple. My test object is just going to be a 1 kilogram mass, and I want to know how much it weighs at different distances from the planet. So at the surface of the planet, that's 1 radii, it's going to weigh 9.8 newtons. At 2 times the distance, it's going to be 2.45 newtons. At 3 times, it's going to be 1.09. At 4 times the distance, it's going to be 0.61 newtons. So this is just telling me how much my same object, my 1 kilogram object, weighs at different distances from the surface of the planet. So the gravitational field strength is the amount of force pulling on a 1 kilogram object at a particular distance from the center of the planet. So we talked yesterday in the video about the 9.8 newtons. And the weight force of my object is 9.8 newtons. And remember that the weight force is equal to mass times gravity. And we know our mass is 1 kilogram, so we were able to convert or calculate little g by doing our 9.8 newtons, our force, divided by our 1 kilogram mass. And little g is equal to 9.8 newtons per kilogram. This is gravitational field strength at the surface of the Earth. If I want to find my gravitational field strength here, little g is going to be 2.45 newtons per kilogram. Here it's going to be 1.09 newtons per kilogram. Here it's 0.61 newtons per kilogram. This is the variable g. The gravitational field strength is just the amount of force pulling on a 1 kilogram object, that's that test object, at a particular distance. So the way we find this is sorry, the calculations that we can do with this is we start with our gravitational force equation, and instead of m1 and m2, mp is the mass of a planet. It could be the Earth. mt is the mass of my test object. And rp is the radius of the planet. So the gravitational field strength, little g, is equal to that gravitational force over here divided by my test object. So I can rearrange this equation to be my gravitational force constant is the mass of the planet, or times the mass of the planet divided by the radius of the planet squared. This formula, this calculation, will give me the gravitational field strength of any particular planet. All right, so this is just, the next couple of slides are just like additional explanation that you don't necessarily need, but I'm going to give them to you anyways. So we have another way of representing the gravitational field strength, and that's using something called equipotential lines. So what it might be is, remember how I had my different weights or my gravitational field strengths at those different distances. Well, each of these lines represents a specific gravitational field strength. So if this one is, say, 1, then this one might be 2, 3, 4, 5, 6, 7, 8. Basically, there's the steps between my two gravitational field strengths are always going to be the same, but the equipotential lines are going to get farther apart. This is just another representation of this inverse square law. The density is larger closest to the surface of the planet and gets much less dense farther away. Now, a physical representation of this might look like this. This is actually taking Newton's law and moving it into Einstein. Einstein explained why gravity acts the way it does. Newton just explained how we can describe gravity. So Einstein's explanation is that anything with mass actually warps space-time. So it's like if you take a bowling ball and put it on a sheet, it's going to create a depression. And the way orbits actually work, or since a mass warps space-time, as something tries to go around it, it thinks it's going in a straight line, but it actually curves. So mass causes a warp in space-time, a curvature, which is what allows things to rotate around it or to orbit around it. And just for fun, because I've always had to say that, remember, this is a two-dimensional representation of something three-dimensional. Well, this is sort of a three-dimensional representation of that. It's showing the warping in 3 dimensions as something moves around. So these were just for fun. But now let's get to what the problems might actually look like. So here's the first example problem. If we have a newly discovered planet that has a density that is 5 times greater than the Earth and a radius that is 3 times the Earth's, what is the surface gravity for the new planet? So to find this, we can still use the one-to-one rule, but we're going to have to use the one-to-one rule because we don't actually have any numbers. We're not being given the Earth's radius. We're not being given the Earth's density. So we have to derive an equation that's going to allow us to find this. Now, surface gravity is going to be little g. Density, where'd it go? Density. The variable for density in physics is rho. That's this weird little p-looking thing, but it's pronounced rho. So what we're going to do is we are going to start with the equation that the surface gravity is equal to the gravitational force constant with the mass of the Earth divided by the radius of the Earth squared. So we're going to put everything in terms of the mass and radius of the Earth. Now, we have to include density because that's the information we're given. So if I look at the density equation, density is mass divided by volume. So I need to be able to find a way to put density in here. Well, I can do that with mass if I have the mass of the Earth and the volume of the Earth. So I can solve this for the mass of the Earth is equal to the density of the Earth times the volume of the Earth. Now, again, volume isn't here, so I can't use volume. I'm going to have to replace stuff here also. So I'm going to do that with this equation. So the mass of the Earth is now equal to the density of the Earth times 4/3 pi, the radius of the Earth cubed. So I can take all of this and substitute into the equation. So the surface gravity is equal to the gravitational constant times, and I'm going to pull out all of my constants when I do this, times 4/3 pi. And let's see, the density, instead of mass, it's going to be density of the Earth times the radius of the Earth cubed divided by the radius of the Earth squared. So this is going to cancel with this, and my surface gravity is going to equal 4/3 g pi, the density of the Earth, the radius of the Earth. All of this is a constant. So when I'm looking at this, the surface gravity is proportional to the radius of the Earth, the density of the Earth times the radius of the Earth. So now if I want to find out what the new surface gravity is, I can use my changes here. So my surface gravity is going to be, the density is 5 times greater times the radius, which is 3 times greater. So my surface gravity is going to be 15 times the Earth's surface gravity. Well, if the Earth's surface gravity is 10, then the surface gravity of my new planet is going to be 15 times 10, or 150 newtons. Now that I've derived this relationship, especially if it's a multiple choice question, I don't have to derive it again. So if I do my next question, this is problem 2, I can use my same relationship. Surface gravity is proportional to the density times the radius. So this time it's 1/2 of the Earth's density times 3/4 of the Earth's radius. And so that's going to give me 3/8 of the Earth's surface gravity. So 3/8 times 10 is going to be 30 divided by 8 is equal to 3.75 newtons. So go ahead and try the problems